Hi, I'm Hamilton, doing it the Kiwi way. There are many different types of transistors out there. You may be aware of the diode, for example. MOSFET is another type of transistor, and it's heavily used in integrated circuits. And you'll see them, well, you won't actually see them, they're so small, but they'll be present in Intel chips, for example, your microwaves, your air conditioning unit. Now, there's two different types of MOSFETs out there. MOSFET stands for metal oxide semiconductor field effect transistor, and this is the N-channel MOSFET. I'll just draw an outline here because that'll show important in a moment. N-channel is preferred over the P-channel MOSFET. The reason being is that N-channel is about 2.5 times smaller and also it's got faster switching speed. We can draw it like this, where we got our source, which is VDD, and this is connected up to ground, and this is our gate. So this is gate, which is here, and then we've got our drain up here, which is this part here, and then we've got our source down here, which is this part here. I won't cover off too much in detail of how this particular transistor works, but basically what happens is that when we apply sufficient voltage at the gate, a channel is formed and electrons can flow between these two, the source and the drain. For pMOS, when there's no voltage or a very low voltage supplied at the gate, a channel is also present and electrons flow. However, when there is sufficient voltage at the gate, there's no flow of electrons here. So by its very nature, nMOS is off when there's a high voltage, and on when there's a low voltage. For pMOS, it's considered on when there's a low voltage at the gate, and when there's a high voltage, the switch or the pMOS is considered off. So this is another way of representing an nMOS, and this is another way of representing a pMOS. Now, what I want to also cover is the substrate, the body. We'll connect it up again. We've got our gate, our drain, our source here. That's connected to VDD, which is amount of voltage applied, and the body is generally connected to the source. For the pMOS, we've got our drain down here, we've got a source, we've got our gate, and we've got a circle here to say it operates directly opposite to the way the nMOS does. And the body is connected straight up to source again. So this is where you might see in schematics, for example, and also a representation like this. We tend to draw them like this. So we've got our gate, we've got our drain, we've got our source. That's connected generally to ground, and this is connected to VDD, which is our power source to drive it. Gate, drain, source. Whoops, I got that around the wrong way. Source, drain, and off to ground here. This is a representation of nMOS implemented on the circuit. This resistor is critical for its operation. It's called a pull-up resistor, and it's essential to ensure that we don't short circuit the battery, and also to make sure we drive the correct answer out through here, and to limit the amount of current, or limit the amount of current, through this transistor. This is another way of representing it.